Hello, this is section 2.5 for Calc AB, and today we're going to be talking about implicit differentiation. So the big idea is, what do you do when you have to solve the derivative when you cannot get y by itself? That's the big concept. So what we've been doing is called explicit differentiation, when y was already by itself. Now this one we could easily solve for y. So if you divide by x, then you get this new equation, and then we can easily do that derivative using the power rule, which is what we did. We moved the x up, x to the -1, and then we were able to do the derivative of both sides. And note that the y we wrote as y prime, or we wrote as dy dx. That means derivative. And then, of course, here's our power rule. Pulled the exponent down, subtracted 1, and there it is. Okay, but the problem is, what if you cannot get y by itself? Can we do the derivative as it is? And the answer is yes. You have to treat y like a function, though. Y represents a function in terms of x. So that's what we're going to practice down here. So here's our expressions, and you notice you just start off the derivative like normal with a 6x cubed because you're doing the derivative with respect to x. So we pulled the 3 down, used the power rule here. And I told you in class and in previous videos, you're always doing the chain rule. So when you pull the 3 down and multiply and subtract 1 from the exponent, when you multiply by the derivative of the inside, well, the derivative of x is just 1. We just don't write that times 1 right there, but it is always there. So carry that concept over to the next problem. Since we're doing the derivative with respect to x, when you do this derivative, you pull the 3 down and multiply, subtract 1 from the exponent. And then just like chain rule, the inside stays the same, but then you have to multiply by the derivative of the inside function. And now, since that's not x, we have to multiply by the derivative, which is dy dx. You could also write y prime there as well. Okay? So that's what we demonstrate here. So x squared turns into 2x, then 5y. Well, 5 is a scalar, so it'll stay out in front, but then y turns into dy dx. And then when we do the product rule here, first times derivative of the second, and notice that I did the chain rule, pulled the 2 down, used the power rule first, and then had to multiply by the derivative of y. And then, of course, plus second times derivative of the first. Okay? Now, this box kind of gives a general idea on how to solve with implicit differentiation, but it's going to be a lot more helpful to look through an example. So here we go. Find the derivative dy dx implicitly. So notice your equation here. First of all, it's not technically a function. If you were to graph this, this would be an ellipse, and that does not pass the vertical line test. And if you were to try to solve for y to get a traditional derivative problem that we've done and do the derivative explicitly, like we're used to with y by itself, you would have to move your x squared over, divide by 4, take the square root of both sides, which would then introduce a plus or a minus, and it's a nightmare to do the derivative. So leave it as it is, and we'll use implicit differentiation. So what you do, start from the left and do the derivative of each term. So x squared turns into 2x like normal, because we're doing the derivative with respect to x. Then when we get here, plus 4y squared, so here's where we'll use the chain rule, pull the 2 down, and so forth. But then notice I have to multiply by the derivative of y. There's the dy dx. Equals, and then the derivative of 4 is a number, so that derivative is 0. So then comes the algebra. So get everything, get your 2x over on this side, divide over the 8y, we're solving for dy dx, and this is the answer. This equation will give you the slope of the tangent line anywhere on that ellipse. And notice it's in terms of x and y, but that's okay. That's perfectly fine. Okay, now let's look at another example. So I'm going to scroll down here. So these are 4 really good problems. So for this one, you just have to realize you have to use the product rule. So that's what we did first, and then the derivative of y turns into dy dx, plus second times derivative of the first. Then when you do the derivative of this part, pull that 3 to use the power rule. But then again, you have to multiply by the derivative of the inside. The derivative of x is 1, and of course the derivative of 4 is 0. And then you're going to quickly learn the calculus is really not the challenging part of these types of problems. It's going to be the algebra, because now you have to get the dy dx by itself. So move everything that doesn't have a dy dx over to the other side. So that's why this 3x squared y is going over here. And then factor the dy dx out of those two terms, which is what I've done. And then last step is to just simply divide by that binomial. Okay, and that's what this box up here walks you through. Do the derivative of both sides with respect to x, collects all the dy dx terms on one side, everything else on the other, factor out the dy dx, and that's what that's walking you through right there. Because that's typically how these problems are solved. Now this one is a good one because when you do the derivative, now I jumped ahead of myself a little bit. First thing you should do is see if you can get y by itself. If you can, you don't technically need implicit differentiation. So you can still use it, but this one, y minus, yeah, there's no way you can get y by itself. And then same thing over here. You have a y stuck within this binomial cubed and then a y squared. Getting y by itself is not a very practical option. So you just start from the left and do the derivative, and just realize every time you have to do the derivative of y, you need to either use the chain rule or multiply, or it turns into dy dx. Okay, so when you do this one, you do the chain rule, pull that 3 down, subtract 1 from your exponent. Now, when you multiply by the derivative of the inside, x turns into 1 plus y turns into dy dx. So be careful, it's a binomial, so you'll need to make sure you put it in parentheses. Then y squared turns into 2y times dy dx, and then 5 turns into 0. Now, with this type of problem, notice you have a dy dx stuck within a binomial. So in order to break it free, you have to distribute in order to break that binomial up. So that's what I've done here. So then I'm to where I have two terms that have dy dx in them. So move what doesn't have dy dx over to the other side, and then factor the dy dx out of those two terms. And then our last step is to just simply divide. And it's messy, but that is the derivative. And it's okay that you have x and y in your derivative. It just means you need both x and y to get the slope of the tangent line on this function. Well, it might not be, it's probably not a function, but on this equation. Okay. Let's see here. Oh, one other note. So I know we've been saying y prime in previous sections when we are finding the derivative, and that's, you can do y prime when you're doing the derivative. The problem is it gets lost really easily. You can see why doing dy dx, oh, that's hilarious, I forgot the d right there. When you're doing your dy dx, it's a lot easier to identify and it doesn't get lost as easily. Sorry, there should be a d right there. Okay, so these are just some more examples that you can look through on your own. And of course, email me if there's a step that you don't understand. Like, Cogswell, how'd you get from this step to this step? And I will happily explain that to you. Now, this notation means the second derivative. So, of course, to do the second, you have to do the first. And noticing we can't really get y by itself, let's go ahead and use this new implicit differentiation concept. So I did the derivative, started from the left, did the derivative of each term. One of the biggest mistakes with these problems is the derivative of 16. Students will write 16, and they won't. Oh, what just happened? Okay, sorry for the interruption. So for this one, again, you cannot get y by itself, so we'll just dive into implicit differentiation. So just start from the left, do the derivative of each term, and as I was saying, that's a really easy mistake, is not doing the derivative of 16. And students will write 16 here instead of 0, so just be careful. Now, solve for dy dx, which is what we've done here. Then from there, now you need to do the second derivative. And what's nice is you've already gotten dy dx by itself. So when you go to do the second derivative, this turns into your second derivative. And then you do low d high minus high d low all over low low. But you cannot leave dy dx in your second derivative. So substitute what dy dx is equal to right there. And then we also don't leave fractions within fractions. So we multiplied by y over y. And then that's where when we distributed, that's where we're getting our answer. Now, I'll get some students who will realize, hey, y squared minus x squared, I had x squared minus y squared is equal to 16. So they might put negative 16 in that numerator, and that's fine. That answer would be acceptable. Okay. All right. Now, this is a good example of if you're not careful, you might not need implicit differentiation. So in this one, notice you can actually solve for y and then do the derivative. So you don't have to use implicit differentiation if you don't want to. So always check to see if you can get y by itself before you do the derivative. Okay. Move me up here real fast. Okay, and then this last example, so find the points at which the graph of the equation has a vertical or horizontal tangent line. So guys, vertical and horizontal tangent lines, that's when, for a horizontal, that's when the slope of the tangent line is 0. Well, we've learned that the slope of the tangent line is the derivative. So if we find the derivative and set it equal to 0, we'll get the horizontal tangent line. Now, if it's a rational function, which is probably what's going to happen, then we'll want to set the numerator equal to 0 to get the horizontal tangent line. And we'll set the denominator equal to 0 to figure out where the slope is undefined, because that's where you're going to have a vertical asymptote, potentially. Okay, so that's what we've done. Now, first and foremost, ask yourself, can you get y by itself? Y squared, 4, no. And it's not worth trying. So, okay, then you're going to dive into implicit differentiation. So you're going to start from the left, do the derivative of each term with respect to x. So all the x's you treat like normal. So 4x squared turns into 8x. But here's where you have to use your chain rule. Y squared, your power rule, but then times the derivative of y. Negative 8x turns into 8. 4y turns into 4 times dy dx, and then the derivative of 4 is 0, of course. Then solve for dy dx. Move everything that doesn't have a dy dx over to the other side. Factor dy dx out. What's left on the right side, or left side, excuse me. Then divide. There's our derivative. So we're going to set the numerator equal to 0, and that's what this is. X equals 1. That's coming from the numerator. That's your horizontal. That's when the slope is 0. And when you set your denominator equal to 0, that's where this y equals negative 2 is coming from. That's when you're going to have an undefined slope. Now, you're not done though. It asked for the points. So now you need to plug x equals 1 back into your original function, which is what I'm doing over here, to get your y value or values. It might have 2. If you look closely, this looks like it's going to be, this would be an ellipse if you were to graph this. So it would make sense. You're going to get 2 horizontal tangent lines, and then you should get 2 vertical tangent lines on your that are going to hit your ellipse. All right. And then that's what we did here. We plugged negative 2 in to our function for all the y's and solved and kind of got cut off there. But there's actually 2 values for x as well. So then I wrote over here, we have our horizontal tangent line at our x value 1 for 2 points. Here's where we solved for our y values. And then our vertical tangent lines right here, both having the y value negative 2. Okay. Now, you need to practice these. You've got to do your homework. The calculus is not the challenging part. It's going to be the algebra and solving for dy dx. So you definitely need to practice these, and please email me if you have any questions. Thanks.